Construction on soft or unstable ground has long been a challenging area of geotechnical engineering practice. Geofoam provides solutions to many of these problems. Geofoam refers to expanded polystyrene, or EPS foam in block or planar form, utilized in geotechnical applications. The unique properties of this closed-cell foam plastic, super lightweight, compressive resistance, durability, and resistance to moisture coupled with excellent thermal performance have resulted in EPS foam proving to be the superior, cost-effective, environmentally responsive solution for a wide variety of geotechnical applications. The widespread use of geofoam began in Norway in 1972. A road constructed over unstable, compressible clay repeatedly settled, regardless of the repair methods. Enter geofoam. Sub-excavation and reconstruction of the roadway over a 2-meter thick layer of geofoam virtually eliminated settling. This initial success led to further exploration of uses and applications for geofoam. Recent examinations, after more than 2.5 decades at the original Norwegian site, show no apparent change in the material's physical properties. A very similar project in the United States many years later has shown equally impressive results. In the fall of 1992, a section of Atkinson Road in Illinois collapsed into a peat bog. This 2-lane stretch of road suffered repeatedly from seasonal settling during periods of high groundwater levels. A dry land bridge, excavation of existing soil, or preloading seemed to be the only solutions. However, all were deemed prohibitively expensive or time-consuming. Enter lightweight geofoam. It was determined to be cost-competitive with other fills and eliminated further expense with dramatic savings in excavation, total materials, and construction time. The stepped construction, along with staggered joints to assure stress distribution, was easy to achieve with the geofoam blocks. Culverts, catch basins, and other on-site structures were easily accommodated by custom fitting the blocks with simple cutting tools. Just 2 days to place the foam and less than 3 weeks overall saw the project complete, and there has been no reoccurrence of settling. It was the use of geofoam in Japan that really began to gain high praise and acceptance for the material worldwide. Between 1985 and 1997, over 1.3 million cubic meters of EPS geofoam were used in more than 2,000 projects, ranging from an interstate highway bypass, where geofoam was used to stabilize the ground under this busy section of road, to the use of geofoam as a super lightweight fill at a bridge retaining wall. Here, geofoam was selected due to its superior ability to absorb lateral pressure. Large-scale testing, conducted by joint government, civil engineering, and industry groups in Japan as well as in Norway, served to evaluate and prove geofoam's superior performance and safety in a variety of geotechnical applications. Geofoam is a proven performer. The application of geofoam in constructing airport taxiways, which must support immense loads, began in Japan and has found its place in the U.S. Traffic at the New Orleans International Airport demanded a dependable solution to halt sinking and the resultant cracking and disintegration of their primary taxiways. Enter geofoam. There, 18,000 cubic yards of geofoam was used. Its superior compressive resistance more than able to support the heavy airport traffic. Concern regarding the susceptibility of geofoam to chemical or solvent attack also needed to be addressed. Typically providing sufficient overfill, a concrete slab, plastic or other suitable lightweight barrier assures the foam is kept separated from potential harm. Versatility is one of geofoam's strongest attributes. In 1987, a section of mountainous Colorado Highway 160 failed and slid down the mountainside due to a rising water table. The repairs undertaken there constituted the first use of geofoam in the U.S. for highway side slope stabilization. Traditional restoration measures for similar failures had proved unsuccessful. Costs for these conventional alternatives were estimated to be in the order of $1 million. The cost of the completed geofoam option was under $200,000. Once again, geofoam's superior properties and cost-effectiveness as a lightweight fill met the challenge. 2 men lifted the 80-pound geofoam blocks and another slid them into place. Add the ease of transporting such a light material to a remote or difficult work site, and you can see where some of the savings were realized. Performance and savings makes geofoam a great buy. The Pyramid Carousel Center in Syracuse, New York, a multi-level shopping mall, is surrounded by geofoam. This large downtown site was considered practically unbuildable. It contained an old oil tank farm and an abandoned landfill, resting on soft foundation soils extending to a depth of 55 meters. In addition, the groundwater level was only 1.5 meters below original grade. Conventional methods were considered for foundation support, but were found to be too costly. A load-compensated mat foundation surrounded by 40,000 cubic yards of geofoam was specified. Soil was excavated and removed to a depth of 5 meters over the building plan area. Geofoam's low cost compared to traditional methods helped make this a truly successful project for this downtown improvement. So successful, in fact, that several years later, when an addition was undertaken, the original geofoam was excavated and reused in the new construction. Tests of the material showed that all of the physical properties still met required specifications. In Hawaii, geofoam was used to create a 21-meter-high embankment for an emergency exit ramp on an interstate highway on the island of Oahu. Initially designed to consist entirely of earth fill with geotextile reinforcement, site conditions encountered during construction were worse than those anticipated. Proposed wick drains of up to 24-meter lengths would penetrate into artesian formations. Enter geofoam. The redesign employed much shorter depths of wick penetration, and 17,000 cubic meters of geofoam were used as soil replacement and lightweight fill. The geofoam effectively reduced settlement and concerns over the artesian pressures. In this perpetually sunny region, exposure to sun or ultraviolet light was a concern. Prolonged exposure to sunlight can lead to discoloration and dusting. But these changes are entirely superficial, and once geofoam is installed and properly covered, they are of no concern. Alaska has proven a perfect place to take advantage of the superior insulating performance of geofoam. Proper planning and design with an understanding of soil, water table, and freeze conditions have achieved excellent results in mitigating problems associated with frost heave and permafrost. At sites that experience seasonal frost heave, geofoam insulation functions to limit the depth of frost penetration. Careful attention must, however, be given to design the road structure with sufficient granular base to minimize possibilities of undesirable differential icing of the roadway.